So I'm going to show you how to prove geometry theorems in GXWeb, the browser-based version of geometry expressions. And I'm going to take the theorems I'm going to use from this book, Machine Proofs in Geometry. The book is written about how to create a geometry theorem prover, but it has about 400 examples that they test their system out on, so it's a useful source for geometry theorems. Now, GXWeb was not written as a geometry theorem prover, but it can be used as one, and I'd like to show you how. So the first theorem I'm going to do is a very straightforward one. The line joining the midpoints of two sides of a triangle is parallel to the third side and is equal to 1/2 the length. So to do that, first of all, I need to draw a triangle. I'm going to use my line segment tool here. We'll draw any old triangle, ABC. Now I need to connect up the midpoints of two sides, so we need to create the midpoints. Let's create the midpoint of that side. Now here, very conveniently, is my midpoint construction tool. There are other ones which we could see if we wanted. However, the software is presenting its guess as to what we want, and it's guessing right in this occasion. We'd like the midpoint of that, and we need to connect them up. So we want to show that DE is parallel to and 1/2 the length of AC. Well, as we have lengths here, I'd like to put some lengths into our triangle. So let's specify the triangle by constraining its lengths. Now, this is where geometry expressions differs a bit from your typical dynamic geometry software, in that geometry expressions is constraint-based. I'm adding here a length of BC. The software is suggesting I use the A, give it a generic length A, and I'm going to accept that. I've trained myself to select the side opposite A first, and it saves me typing. This is B, and I'll let that be C. So these are generic quantities, but they have numeric values, and those numeric values can be observed in this numeric panel. By default, they're locked, which means that when you drag things around, they stay in place, but you can unlock them. And if you unlock them, when you drag things around, the values change. Now we're going to want to look at the length of DE and the length of AC. So we can just type that in, distance AC. Now this, of course, is giving us a numeric distance. We're in the numeric panel. Now add another one, distance DE. So we could observe that this is in fact half of this. So we can watch as we drag things around, changing the values of A, B, and C, that these change, and that this half actually stays. But we haven't actually proved the theorem, we've just observed the results of the theorem. To prove it, we go into the symbolic panel down here, where if we ask for the distance, we know, of course, that the distance between A and C is B. What is the distance between D and E? And we say that's B over 2. So this constitutes a machine proof of the theorem. Oh, the other part of the theorem is that the two lines are parallel. We can ask for the angle between DE and AC. Now, a point here is that the name of any line segment is just the names of its two endpoints, but in alphabetical order. It wouldn't have done for me to type CA. It has to be AC. And we see that's 2 pi. These things are parallel. So that's my first theorem.